Hello. Is the audibility visibility clear? Please let me know if the audibility visibility is clear or not. So yes, so what I was saying is that sorry for the small disruption. Sorry for the small disruption. Okay. So my dear friends, yes, we are going to start with the queuing theory, and you know that queuing theory is one of the most important chapters when it comes to your industrial engineering, right? So without wasting any time, let us see what is. So here we are going to analyze the system of queues. Here we are going to analyze the system of queues, and when there is queue, so there remains, there is the system, and then queue plus the person taking the service will constitute about your system. And then you have different formulas, like everyone thinks that queuing theory is all about formula, like there is length of the system, length of the queue, and then there will be waiting time, and then there will be probability, steady state probability formula. All those things are there, but the chapter starts with the two most important distributions, and that you think means that you should know very well. The chapter starts with two important distributions, and that is, my dear friends, Poisson distribution, right? So what is Poisson distribution? Let us see. My dear friends, the probability of X customers, the arrival rate of X customers, the probability that X arrivals is there in unit time is given by this formula. So what is this formula? This is the probability of X arrivals in unit time. Probability of X arrivals in unit time. Probability of X arrivals in unit time. And you will also see this formula. Probability of X arrivals in time t. Probability of X arrivals in time t. So what is the difference between these two? This is the probability of X arrivals for unit time. This is for unit time, and this is for X arrivals for time t. Obviously, very easily you can see that when t I will make as 1, so it becomes the formula for unit time. That is fine. So as far as this formula is concerned, the number 1 formula is concerned, you will see this very often in your engineering maths, right? And as far as this second formula is concerned, you can see mostly in industrial engineering, and this formula can also be used, but both the formulas you will see in industrial engineering. So let us try to see that how these formulas are used, and obviously this is the Poisson distribution, where lambda, what is the mean and variance for Poisson distribution? This is the lambda, where lambda is the mean, and this is also equal to variance. This is lambda equal to mean and also equal to variance. And over here it is the average arrival rate. Average arrival rate. Average arrival rate. So in most of the questions you will get lambda only. They will give you lambda. In most of the questions you will be getting lambda. Now I'll try to explain you what is arrival rate and all those things. For example, here is a person sitting and he is providing service to the customers who are coming. Here is the customers who are coming, and after taking the service, the people will leave the facility. People will leave the facility. So assume that people are coming at the rate of 20 per hour, and people are leaving the service at the rate of 30 per hour. Yes, mu should be greater than lambda. For an efficient queuing system, mu should be greater than lambda. So this is the arrival rate. This is what lambda is, the arrival rate, and mu is the departure rate. I can also think in this way that "20 persons are coming in every 60 minutes. 20 persons are coming every 60 minutes. So 1 person is coming every 1 into 60 by 20, that is 3 minutes. So 1 person is coming every 3 minutes, every 3 minutes. Similarly, I can say that you are providing service to 30 people every 60 minutes. So you are providing service to 1 people every 2 minutes. So this 3 is nothing but your inter-arrival time. Inter-arrival time. And this 2 is nothing but service time or departure time. So you can see 4 things that I have highlighted. 4 things I have highlighted. So out of these 4 things, what is lambda? Arrival rate. What is mu? Departure rate. What is 3? Inter-arrival time. And what is 2 minutes? Service time, right? So most of the cases you will find lambda. Most of the cases you will find lambda. They will only give you lambda, and that is your arrival rate. In Poisson's formula, in exponential formula, the lambda that you are seeing over here, that is the same lambda. But he could have also given the question like the inter-arrival time is 3 minutes, and then they could have asked you for any, for example, probability of 4 arrivals in some minute. So then you have to calculate lambda from here only. But you should know that, okay, this is the same lambda. So we say that arrival follows Poisson distribution. The first line in queuing theory that you need to remember is arrival follows Poisson distribution and service time follows exponential distribution. Yes or no? Service time follows exponential distribution. So arrival rate follows Poisson and service time always follows exponential distribution. You should know that most of the time related phenomenon, they are exponentially distributed, and details of it you will study in engineering maths, but I will give you the concept that what is exponential distribution. So you must have studied that probability of time is nothing but the function, the PDF. The PDF is given by lambda e to the power minus lambda t. Now what is PDF? The probability density function. Because it is a continuous distribution formula, so PDF we say, the probability function in continuous functions are called as PDF. And this is for t greater than 0. This is for t greater than 0, and this is 0 for t less than 0. So t greater than or equal to 0, this is the PDF. So now my dear friends, see one thing. If he asks you that probability that time is in between t1 to t2, if he asks like this, so what I will do, I will simply integrate the PDF. I will simply integrate the PDF. I will simply integrate the PDF between t1 and t2. So what will we get? Lambda e to the power minus lambda t by minus lambda t1 to t2. So this is minus e to the power minus lambda t2 minus e to the power minus lambda t1, and finally we have e to the power minus lambda t1 minus e to the power minus lambda t2. So this is the formula. So either you can remember this or you cannot remember this, that is up to you. But you should know that when he is asking you about the probability of arrivals, then you will use which formula? The Poisson's formula. when he is talking about the probability of arrivals, which formula should you use? The Poisson's formula. For example, lambda will be given as 20 per hour, and what is the probability that x arrivals is following in unit time, or x arrivals is coming in time t, something like that. And when will you use this formula? That is the exponential formula. You will use when he is asking question with respect to time. He is asking questions with respect to time. Okay. I'll give you examples, no need to worry. Now the question here is how to use both the formulas. That is our second topic. I have given you the concept that okay, these two formulas are there, but now how to use this formula? When will this formula be used and when will this formula be used? So let us see some examples. Let us see some examples. Now what he is saying? He is saying that in a bank, customers arrive at the rate of 10 per hour. Now see, I told you that they will always give you lambda. So lambda is what? 10 per hour. And one more thing before I take this question, the lambda which you know in queuing theory is the same lambda that is used in Poisson's and the same lambda that is used in exponential. Both lambdas are same only. Okay. So lambda is 10 per hour as per Poisson's distribution. The probability of 6 arrivals in any given hour. What he is asking? The probability of 6 arrivals. So x will be what? 6. And in any given hour, that means it's a unit time. Any given hour means what? Unit time. 1 hour he is talking about, and lambda also he has given in terms of hour only. So very easily I can apply probability of x arrivals in unit time is given by e to the power minus lambda, lambda to the power x by x factorial. Why? Because lambda is given in hour, unit time is there. So very easily I can use. So e to the power minus lambda is what? 10. Lambda is 10 to the power what is x? That is 6, and divided by 6 factorial. So if you simplify this, you will get the answer, right? And now my dear friends, read this question. Read this question. In a bank, customers arrive at the rate of 10 per hour as per Poisson distribution. The probability of 6 arrivals in a span of 30 minutes. Now my dear friends, the time is not unit time. The time is not unit time. He is asking in a span of 30 minutes. So x arrivals in some time t. What is the formula? X arrivals in some time t. X arrivals in time t is given by what? E to the power minus lambda t and lambda t to the power x divided by x factorial. So x you know, that is the 6 arrival, but we have to calculate lambda t. Now my dear friends, one thing you have to note very clearly, that lambda is what? It is 10 per hour, 10 per hour into t is what? 30 minutes. So tell me one thing my dear friends, can we cancel hour and minutes? Can we cancel hour and minutes? No, we cannot cancel hour and minutes. That means we have to convert it in same time. In the denominator here is hour, in the numerator here is minute. We cannot cancel both. There has to be same consistency in time. So I have two options. Either I convert 30 minutes to hours or I convert hour to minute. Anything I can do. So for example, if I write over here that 30 minutes corresponds to 0.5 hour. So I have converted to hour. So then I can write 10 by hour into 30 minutes. In place of 30 minutes I am writing 0.5 hour. So hour and hour now gets cancelled and I am left with 5. Or you can do one more thing, that or you can do one more thing, that lambda is given 10 per hour. So what I can do? In place of this hour, I can write 60 minutes. I can write 60 minutes into 30 minutes. So again I am left with 5. So by both the concepts you will get 5 only. Or you can do one more thing. In before only you convert it in lambda, you write in terms of minutes. Before only you write lambda in terms of minute. I will show you, don't worry. What is lambda? 10 per hour, and you want to convert everything in terms of minute. So I will show you. For example, he is saying that lambda is equal to 10 per hour. So what it means? It means that in 60 minutes, how many persons are coming? 10 persons are coming. So I want to convert lambda in terms of minute. So in 1 minute, earlier it was in 1 hour. So now I am writing in 1 minute. What is the lambda? 10 by 60 or 1 by 6. So now you have lambda 1 by 6 per minute. So minute is there, and now I can very easily put 30 minutes. Now I can very easily put, that means now 6 arrivals. The question was 6 arrivals in 30 minutes. 6 arrivals in 30 minutes will be what? E to the power minus lambda t to the power x by x factorial. So lambda t is equal to what? Lambda t equal to, now I have put what? And now I put in terms of minute. So 1 by 6 I am writing into, now I can put t is equal to 30 minutes. So this is also per minute, this is also minute, minute gets cancelled and it becomes 5. So either way you do, it will be 5 only. What I want to say, either way you write, it will be 5, but just maintain consistency of unit. And when everything is known, you can very easily write e to the power minus 5 to the power 6 by 6 factorial, right? So this is the thing you need to understand, and now I think there is no confusion as far as your units are concerned, right? So at least, my dear friends, before solving the question, I hope that you got to know that he is asking about this Poisson's formula. There are two probability formula in queuing theory. One is discrete in nature, one is continuous in nature. So this is the discrete formula. Poisson is discrete in nature. Arrivals, number of arrivals will be discrete only, 1, 2, 3, 4, 5. But when he is asking with respect to time, so time cannot be discrete, it is continuous. So then we will use the exponential formula, and that you have to guess by your understanding of the situation only. For example, he was asking about probability of 6 arrival. So arrival is discrete in nature. But now what he will ask, and it's a gate question, so please read the question once. He is asking that the arrival of customers over fixed time interval in a bank follow Poisson distribution. Yes, you know that arrival follows Poisson with an average of 30 customers per hour. Yes, with an average of 30. So I told you already that lambda will be same in both the cases, no surprising. So I will write here lambda is equal to 30 per hour. The probability that the time between, see my dear friend, this is the thing that you need to check. He is asking probability with respect to time, and time between successive customer arrival is between 1 to 3 minutes. So just by reading the question, you are knowing that he is asking probability of time, and time will follow what? Exponential distribution. So don't go by that. The first line will say you that arrival follows Poisson, that we know. But he is asking question with respect to time, and that is the thing that we need to focus over here. So you know which distribution is going to be used. We are going to use exponential distribution. We are going to use exponential distribution. So what is the PDF? What is the PDF for it? It is lambda e to the power minus lambda t. But you know what we are going to do when we integrate? When we integrate, we are going to get the probability. Integrating the PDF will give you probability. Integrating the PDF will give you probability. That's what I have done. Yes or no? That's what I have done over here. See, when I integrate the PDF, I will get the probability. So directly I can use this formula. Directly I can use this formula. So what is the probability between T1 to T2? So obviously I am going to integrate between T1 to T2 lambda e to the power minus lambda t dt. And what I am going to get? You know already the result, e to the power minus lambda t1 minus e to the power minus lambda t2. This is between 2 times 1 and 3. So what to do? You simply put T1 equal to, you know T1 is equal to 1 minute and T2 is equal to 3 minutes. Now my dear friends, one thing you should be focused or cautious about, that lambda he is given in terms of per hour and you have time in terms of minute. So can hour and minute be same? Again the same problem that we faced in our Poisson. Can we put together? No. So what to do? Convert it in same. So let's say you want to convert in minute. You want to keep everything in terms of minute. So let us take it to the next page. Lambda is 30 per hour and T1 is 1 minute and T2 is 3 minutes. And what is the probability that time is in between T1 to T2? It is e to the power minus lambda T1 minus e to the power minus lambda T2. Right, e to the power minus lambda T1 minus e to the power minus lambda T2. So again the same thing that whether lambda into T, whether lambda into T, it should be consistent. So my dear friends, as we discussed that we let us put everything in minute. So lambda is in hour, we have to convert it in minute. Okay. So in 60 minutes, 1 hour matlab 60 minutes, in 60 minutes 30 customers are coming. So in 1 minute, 1 into 30 by 60, that is 1 by 2 or 0.5 customers are coming. So lambda is either you say 30 per hour or you say 0.5 per minute, both are same only. So now I have converted and I can put here minus lambda is what? 0.5. What is T1? 1 minus e to the power minus what is lambda? 0.5. And what is T2? T2 is 3 minutes. So it is e to the power minus 0.5 minus e to the power minus 1.5. Now when you solve this, you will get the correct answer. So I think the confusion for these distribution formulas, that is Poisson's and exponential, is crystal clear, and now when you attempt the question, you will not face any difficulty while solving it. So these were the first important things as far as we have to discuss the queuing theory, right. Now my dear friends, the second thing that you need to remember in queuing theory is the notation. The notation that you are seeing, that is what the notations are representing. So this thing you have to understand, that A is the arrival, then service time distributions, then C is the number of parallel servers, that is the queue discipline, and from here only question can come, that they will give you this system and they will ask you that what does C and D represents. So C represents the number of servers and D represents the queue discipline. So that is the thing that you need to see. Now my dear friends, the model that has been, that will be asked or has been asked in the past is that always they will give you this, where the number of servers is 1, the distribution followed is Markovian distributions, and let us say this is the general discipline, but the important thing over here is this one, that is there is maximum number allowed in the system is infinite. Maximum number allowed in system, maximum number allowed in system is infinite. That is the thing that you need to focus on. What is lambda? Lambda is the arrival rate. Now from here the formula series comes, that means the formula that you have been already reading in queuing theory and you have been remembering. What is lambda? Lambda is the arrival rate. What is mu? Mu is the service rate or departure rate, I can write. Departure rate. So the first important thing is utilization factor. So what is the utilization factor? Utilization factor or rho that we say is lambda by mu. Lambda by mu, obviously it has got no units. And my dear friends, the steady state formula. Now you know that I will write length of the system, then length of the queue will come, time taken, all those things will come, but the most important formula from where it has been derived is steady state formula for probability of n persons in system. Steady state formula for probability of n persons in system. That is the important thing. And you know the formula is given by probability of n persons in system is given by P naught into rho to the power n. P naught into rho to the power n. So for example, this is the formula. So for example, if we ask you what is the probability of one person in the system, so you write rho P naught, where P naught is the probability of 0 persons in system. 0 persons in system. So if you want to find P1, you will get rho P naught. They can ask you what is the probability of 2 persons in system. So you will write what? Rho square P naught, and similarly you can find. So you know one thing, that the probability that there is 0 person, there is 1 person, there is 2 persons, and since you have infinite number of persons in the system as per this model, so last number will be infinite, that is equal to 1. That is equal to 1. So if you put all these formulas, I am simply writing the main formula that you will get is P naught is equal to 1 minus rho. P naught is equal to 1 minus rho that you will arrive at. Right? So you can put here and apply the formula, you will get it. And after that, the next thing that comes is length of the system. Length of the system. So what is length of the system? You know that is rho by 1 minus rho, yes or no? Rho by 1 minus rho. Then comes what is the length of the queue, length of queue. So length of the queue will be rho square by 1 minus rho, rho square by 1 minus rho. Then there is time taken to wait in system. Time taken in system, the time is given by Little's law, it is given by Little's law. So time in the system is given by length of the system by lambda, and time taken in the queue is length of the queue by lambda. So this is the Little's law. Then they can ask you what is probability that system is busy. System is busy, that is equal to rho, and what is the probability that system is idle, that is equal to 1 minus rho, right. Now all these formulas are there. For example, you will also get to know that what is the probability that there is more than k people in the system. All those formulas you will memorize, that is not the big deal. But the thing is that questions can come from one more model also, that is when there is some particular number in the system. Yes, when there is some particular number n in the system, maximum number of customers allowed in system. Maximum number of customers allowed in system. Maximum number of customers allowed in system is n. So remember that now also the steady state formula of probability will be applied. Now also the steady state formula of probability will be applied, but now there will be P naught. If I have to do the summation probability equal to 1, so there will be P naught plus P1 plus P2 and dot dot dot, it will be till Pn, it will be till Pn, the sum will be equal to 1. Not earlier it was infinite, but now it is Pn, and when you solve this completely, here the P naught formula that you will get is, that is important and that you should memorize. You should memorize is just a minute. Yes. So the formula, let me write in the next page. The P naught formula that you will get and you should memorize is 1 minus rho by 1 minus rho to the power n plus 1. It has been obtained from GP formula series, that is not the thing, but this is only possible when rho is not equal to 1, right. So this formula is there, and what if it is equal to 1? So this will become 1 by n plus 1. 1 by n plus 1 when rho is equal to 1. So what is n? N is the maximum number of customers allowed in the system. What is n? N is the maximum number of customers allowed in the system. So this is P naught. And one more thing, they can also ask you, this is one formula, they can also ask you what is the length of the system. What is the length of the system? What is the length of the system? So concept is same, but the way of derivation is same, but the formula is a bit lengthy one. So I am writing the formula, and if possible you can memorize this. I know it is a big formula that I am going to write. Yes. Yes, so this is a bit lengthy formula, but if possible you can memorize it. So this is for rho not equal to 1, and if rho is equal to 1 it will be n by 2. If rho is equal to 1 it will be 1 by 2. Who knows, this might come that when rho is equal to 1 the length of the system is what. So you can write n by 2. So these are the things, my dear friends, that you need to consider in queuing theory, and at least you should remember these set of formulas, right. And now we are going to start with the next chapter, that is inventory. Now we are going to start with the next chapter, that is inventory, right. So inventory will be, today I will start it, and it will be continued tomorrow also, but let us see if you can complete one model at least today. Just a minute. Okay. So my dear friends, the inventory chapter, it starts with the concept of four types of costs. Four types of cost, that is your unit cost. Unit cost is cost of the item. Cost of the item. In inventory you will purchase your items, and for purchasing the cost of per item will be your unit cost. Very easy. What is ordering cost? It is cost per order. By the way, unit cost is generally denoted by either CU or P naught, anything is fine. What is ordering cost? Cost per order. So it will be rupees, cost per order. So rupees per order, right. What is holding cost? Holding cost, what is holding cost? It is the cost incurred when you hold your inventory. It is the cost incurred. So it will be rupees per unit. The unit will be per unit or item, per time. You might be holding some inventory for a certain period of time, that's why per time will come into picture. And what is back order cost? It is the cost incurred when you took some back order, right, or when you had some shortage. So either it is called shortage cost or it is called back order cost. Again its unit will be rupees, same as holding cost. it is rupees per unit per time, right? So these are the types of cost that you will incur in your models of inventory. And when I say models, you know that two types of model you study in inventory, that is your deterministic model and probabilistic model. So first we are going to see all the concepts of deterministic model, rather I would say the formulae, and then we will discuss the two models of probabilistic models. So if we discuss this, then our inventory is done. So my dear friends, this is the first model, that is the basic model, which is also known as Wilson-Harris model or infinite replenishment model. And you know that these are the assumptions that you are going to make in your basic model. That is, your demand should be uniform, right? Throughout the year, you know that I have this much of demand to cater on. The unit cost is fixed, that means you will not give any discount. By the way, discount model is also there, which you should focus on. Lead time is 0. What is lead time? Lead time is when you place an order. When you place an order, so the time which is being taken to receive the order, the gap is known as lead time. So obviously, when you place an order over here, you will get the next moment itself. That means no lag is there, lead time is 0. No buffer and safety stock. Obviously, in basic model we keep no buffer, and separately we study, that means right after this only we will study shortage model. No shortage, obviously, and cycle time is same. So cycle time will be kept same only, right? So my dear friends, what is the infinite replenishment model? The infinite replenishment model is that, let's say you have some Q units, you have ordered some Q units from somewhere, and now you are going to utilize it. Now you are going to utilize it. So when you utilize it, you are going to utilize at the same pace, at the same rate, you are going to consume. Obviously, it will not go below this. It will not go below this, because then it will become shortage model. So at the same rate, and when you place an order over here, at this point when it got over, immediately someone sent you all the items, and then again it will go and get consumed at the same pace, right? So this is a cycle that we are talking about, and this time is known as cycle time. This time is known as cycle time. This is the Q, that is the inventory that you have ordered. The inventory that you have ordered, that is the Q, and here is the demand rate or consumption rate. Demand rate. So let me demand rate. Okay, let me write fully. Demand rate or consumption rate, and that is, let me write it with small d. It can be capital D also. But most importantly, what is the unit? Most importantly, what is the unit? Its unit is D per time. See, whenever someone says rate, it means we have to divide it by time, velocity, distance by time, acceleration, velocity. So whenever time rate is there, per time will come. So it can be what? It can be your D per year, or it can be D per month, or it can be D per day. Anything is fine, as long as it is rate, anything is fine, right? And don't forget the annual demand he will give you. For example, he is giving you that annual demand is 12,000 units. So this is what? This is 12,000 unit per year, na? Annual demand he has given. So units per year, So this is the same D. This is the same D. Either you can use this D also as your rate, no issues. But if you want to convert it in days, so year, say you have to convert it in 365, you multiply, and then you will get days. Or if you want to convert it in months, so you multiply with 12. But that is the same only, the same demand only that is given in the question, right? So two types of cost that you will incur over here. There is two costs. So total inventory, let me discuss total inventory cost over here. total inventory cost that you incur. First is the ordering cost. First is the ordering cost, and then is the holding cost. Also, this can be said as total variable cost, because these are the things that is varying. Your item cost is not varying, so I might not consider it over here, but generally we should focus on the thing that is varying, because then that only will give us the optimal value. So ordering cost is what? Ordering cost is number of orders into cost per order. And what is holding cost? Holding cost is average inventory into CH, that is the holding cost. So what is order number of orders? Number of orders is annual demand is D, and per unit time you are ordering, let's say Q. On one order you are ordering Q. This is the number of orders into cost per order. And what is average inventory? Average inventory is given by one formula. I'll write that formula, but as of this is Q by 2. As of this case, it will be Q by 2 into CH. Now I will tell you how average inventory will come into picture. So let's say that this is the one cycle that I am analyzing. This is the Q and this is the cycle time, that is TC. So tell me one thing, average inventory means it will be somewhere along this line, because your inventory is varying. So I need to take an average value of inventory. So area will be same. So area under the triangle must be equal to area of rectangle. So what will be area of under the triangle? Half into base, and the height is Q, and area of rectangle is Q average into TC. So TC and TC gets cancelled, so Q average will be, average inventory will be Q by 2. So the same logic we can apply everywhere. That is not the thing. And one more thing, from here only I can write, Q average equal to one more formula you are getting, area under, this is the area of the triangle, that means area under the inventory, actual inventory. That is the triangle I am talking about, divided by what is TC? TC is the cycle time. So in upcoming models you will find different areas under actual inventory. Your inventory is present during which time, that area you have to consider. You just have to see that where inventory is present, and you will take that area divided by cycle time. So I'll show you when we discuss shortage models and when we discuss production model, all those things we will discuss in detail. Yes, so this is the total inventory cost. So this is your total inventory cost. So what is your total inventory cost? It is equal to D by Q into C naught plus average inventory into CH. And for optimum value for optimum, or I should say your objective is to minimize the TVC. Minimum or optimal both are same only. For minimum value of TVC, you should differentiate TVC with respect to the variable, and variable over here is Q. TVC you will differentiate and put it equal to 0. So when you differentiate, it is minus d by q square into C naught plus CH by 2 is equal to 0. So d by q square C naught is equal to CH by 2. So from here only you will get Q, and that you say as Q star as equal to 2d C naught by CH. That is the basic formula of inventory that we have to remember. And the observations is this, that when you substitute this Q star over here in the ordering cost and over here in the holding cost, so you will get the same value of ordering cost and holding cost, the same value as ordering cost and holding cost. So this is one observation. Second, when you substitute, see, you differentiated this for minimizing TVC. So when you substitute this Q over here, the TVC that you will get is minimum, and let me call this as TVC star, and that value you will get as 2d C naught into CH, 2d C naught into CH. So this TV star is nothing but the combination of ordering cost and holding cost, and these two are same. So that means the value of ordering cost and the value of holding cost must be equal to what? Must be equal to ordering cost and holding cost are same. So this is nothing but by 2. It should be nothing but by 2. By by root 2, 1 by root 2 d C naught CH by 2. So if you add this, you are going to get this, right? So two formulas that we memorize over here is one is the Q star and another is the TVC star, Q star and TVC star. That is the minimum inventory cost, or variable cost also we say, and that is the economic order quantity, that is the Q star that we say, right? So these two formulas are there. Concepts is fine, that in every model, in same model. Now tomorrow when I take up shortage model or production consumption model, the same logic I will apply, that I will write all the cost first, and with respect to variable I will differentiate. So with respect to variable, when I differentiate, I am going to get minimum. So every model, some formulas are there, and that's it. You have to remember only that's it. But one more thing, cycle diagram you should never miss. Cycle diagram you should never miss, because questions are coming, questions can come from the middle itself. So just know that, okay, how the cycle formula is being applied. For example, if you consider this triangle if you consider, so how much quantity you have? Q. What is the time period? This Q quantity only that you are ordering, you are consuming over TC. The quantity that you are ordering over here, that you are receiving over here, Q, that is only you are going to consume, over your cycle time. So what I can write? Q is equal to, simply apply the slope formula, small d or capital D, anything, into your TC. So what I have done, I have simply applied the slope formula, slope equal to dy by dx, since it is the rate equal to dy by dx. So Q is equal to d into TC. So tomorrow we are going to continue from here only. here only. So today what we discussed, I suggest everyone to go through the session. Today we discussed about queuing theory, we discussed all the important concepts of queuing theory, and this much only you need to remember. And also I started with infinite replenishment model. So tomorrow for the I'll start with at this point only, from this point, following the inventory models, 3 inventory deterministic models and 1 probabilistic and 2 probabilistic models. So tomorrow I can say that inventory will also be over, right? So my dear friends, I hope you are you are studying well, revising well. Go through these sessions, the earlier sessions also you go through. In case of any doubt, you can just drop your comment in the chat box, right? So all the very best, good luck, take care, bye.